Now, question number 6, it states that two elements V and W are in adjacent groups of the periodic table. So that's the first. I think this question is related to inorganic chemistry. So that's the first statement. So, for example, if
Okay.
V is in group one, then W would be in group two. Now, V reacts with oxygen to form an acidic gas. Uh, so that means that the oxide is acidic. Uh,
So, what is the meaning of adjacent kind? Like, I don't get it.
Adjacent
Like,
groups. Like
adjacent.
if V is in group six, the W would be in group seven.
So that would be parallel, right? Not.
हाँ हमारे adjacent साथ साथ ना ठीक है अच्छा so V reacts with oxygen to form an acidic gas. What does that mean? It means कि it's either अच्छा it's a non-metal because non-metal oxides are acidic. For example, sulfur oxide is acidic, phosphorus oxide is acidic. Metal oxides are basic. So that means V is a non-metal. It's definitely a non-metal because it's forming an acidic oxide. Uh, and that acidic oxide is known as X. So it's a non-metal oxide, that's X. And then V forms an anion with the formula of VOM minus 1. So it has a charge of minus 1. So what we can do is we can think of substances that have a minus 1 charge. Non-metal oxides or non-metal anions that have minus 1 charge. One example that comes to mind, and I only have one example in my mind, that's NO3 minus 1, or it could be NO2 minus 1. Because the other ones, they're all other non-metal anions, they're usually minus 2 or minus 3. For example, sulfur is minus 2, or SO3 is minus 2 as well. Phosphorus is minus 3. So it probably can't be any one of those. So we still have no confirmation. So that's just my hunch. It's either NO3 minus 1 or NO2 minus 1. Now W is also reacting with oxygen to form an acidic gas. So that means W is also an acidic. It's an acidic oxide. And it's forming the acidic oxide which is known as Y. And W forms an anion with a charge of minus 2. Now the only, I mean, there are a couple of possibilities. One is like which polyatomic anion has a charge of minus 2. So it could be carbonate, that's CO3 minus 2. That's one that we have studied. It could be sulfate, SO4 minus 2, or it could be sulfite, SO3 minus 2. So these are the candidates that come to my mind. And they're all in adjacent groups. Like nitrogen is in group 5, carbon is in group 4, sulfur is in group 6. So they're all in adjacent groups. The next part is that a solution of this thing forms a white precipitate Ba2 plus but shows no visible reaction with Mg2 plus. This one is definitely a sulfate because what you have studied in your syllabus is you've in group 2, okay, in inorganic chemistry, what you have studied in inorganic chemistry, you've studied the solubility of sulfates. The solubility of sulfate is that the first one, MgSO4, that is soluble, whereas as you move down the group, the solubility starts to decrease. Calcium sulfate is not that soluble, it's partially soluble. Strontium sulfate is insoluble, and barium sulfate is very insoluble. So the last two are going to form a precipitate. This one is partially soluble. So some of it would dissolve, some of it would not dissolve. The first one would dissolve. So the question had stated that the sulfate ions forms a precipitate with barium ions. That means it's insoluble. And the sulfate ions, they have no visible reaction with Mg2 plus. So this is something that you have studied in your course. It can't be a carbonate because all carbonates are insoluble. If it was magnesium carbonate, it would have been insoluble. If it had been barium carbonate, that would be insoluble as well. If you remember the solubility table, carbonates are all insoluble. except for group 1 and NH4 plus 1. Otherwise, carbonates are all. So I'm going to get rid of carbonate. That's no longer an option. Now the question is stating that we need to identify a value for V, X, M, W, and that's it. I mean, that's the whole question. I think it's a 6-mark question. It's a small question. So we need to identify the value. So what's V? V is probably nitrogen. And what's X? He's saying it's forming an acidic gas. The acidic gas is NO2. Uh, that's the gas that would be formed by V. What acid would it form? Why is it acidic? Because it's going to form nitric acid or nitrous acid if you mix it in water. Uh, what is M? M is probably either. I mean, I'm hoping that in the marking scheme they gave an option. It could be a nitrate ion or it could be a nitrite ion. So I'm taking M as 3. I'm taking it as nitrate. ठीक है, because I don't think they've given us any other information, so we can't really figure out whether it's going to be NO3 minus 1 or whether it's going to be NO2 minus 1. ठीक है, we're going to check that in the marking scheme, this one. ठीक है, I'm taking it as 3 because nitrate is more common. What about W? W is definitely sulfur. So W is sulfur, and what's Y? That's an acidic oxide that's formed when W burns. So that must be sulfur dioxide. And the last one is they're asking for. Okay, just 1 second. The board is hanging up. Let me reload the board. See, this one is SO2. And N is going to be either SO4 minus 2 or it could be SO3 minus 2. So I'm going to take N as 4. Just 1 second. The board is still not here.
Sir, why not 2? Why 4?
नहीं, SO4 ये कौन सा आयन होगा? सल्फेट. इट्स सल्फेट होता है.
Sulfuric acid, sir.
नहीं, this ion. W is S, right?
Yes, sir.
So which ions have you studied? It's either SO4 minus.
4 and 3.
Okay, these are the only 2 that you have studied.
Yes.
Just a second, still not loading. But the board is gone. So we're going to just confirm with the marking scheme. Okay, because we had confusions with 4 and 3. So I think it was the next. Okay, so they had actually given both options. And over here as well, it was SO2, so they had given multiple options. So the board has stopped working this one. Now, in the next part, he's saying that by referring to enthalpy changes, explain why this forms a wide pressure with barium ions but shows no visible reaction. We just talked about that solubility of sulfates decreases down the group, and it decreases down group 2. So MgSO4 is soluble, but barium sulfate is not soluble. And the question is actually a lot more complicated, actually. It's not that simple. Because to answer this question, basically he's asking for an explanation for this. And remember, you're going to get a typical question like this a lot of times. where you have to explain this. Now, what is you have to use enthalpy changes to explain this. Now, what you're going to do is when you have to explain this, I'm going to explain everything in detail now. Okay, that's related to lattice enthalpy and enthalpy of solution. So when you mix something in water, okay, for example, if you're trying to dissolve MgSO4, MgSO4 is solid. You mix it in water, it dissolves in water and ends up forming aqueous ions. It dissociates. So this is enthalpy change. The enthalpy change of this reaction is going to be called the enthalpy change of solution. It's going to be referred to as the enthalpy change of solution. So what is the enthalpy change of solution? What happens when an ionic compound dissolves in water and dissociates? An ionic compound is basically a bunch of positive ions and negative ions all attached to each other. So there's positive ion in this, and there is negative ions. Okay, let me just see if the website has started working again. Acha, so it's a bunch of positive ions and negative ions all joined up, very strongly attracted to each other. When you mix them in water, the ions dissociate, they break and they scatter in water. The positive ions and the negative ions, they all scatter. I mean, that's what happens when you stir, when you move your spoon vigorously in water, you're trying to dissolve a salt, the ions scatter. And the ions, they get completely surrounded by water molecules. All these tiny water molecules, all these tiny water molecules, they then come and they surround the positive and the negative ions. So that is how ionic compounds. I said that is how ionic compounds dissolve. Yeah, lattice, it dissociates. Okay, you move a spoon through the solution, like if you're dissolving NaCl crystals, the ions, they get scattered and they mix with water. So this is the whole process. MgSO4 solid gets mixed and dissociates. But there's another path. So if I break this into path, in the first step is going to be step number 1. You break the ions and you separate the ions by a vigorous stirring. So the positive and the negative ions, they dissociate, they break up. That's known as lattice enthalpy. That's the negative of lattice enthalpy or lattice energy. Lattice energy is, or the negative of lattice energy is when you break a lattice and you break it into ions. And the next step is those gaseous ions, they get surrounded by water molecules to form aqueous ions. And that is known as enthalpy change of hydration. So your enthalpy change of solution is basically one path. If you remember Hess law stated that one path, the energy change of one path is the same as the energy change of the other path, as long as you're making the same thing. So I'm just going to repeat: dissolving an ionic compound and making aqueous ions. When you dissolve it, it requires 2 steps. One step is you break the lattice. I mean, this tiny crystal. You move your spoon vigorously so that the ions, they get scattered, the ionic bonds break, and the Mg2 plus and the SO4 minus 2 ions are no longer together because you're stirring it so vigorously. And the next step is those ions, they get surrounded by water molecules and they turn into aqueous ions. So it involves 2 steps. So enthalpy change of solution is basically equal to it's equal to the negative of lattice energy plus delta H hydration. So that's your relationship that you have for ionic compounds. So this over here is the relationship. Now what happens? Just 1 minute break. Take just a minute. So let's start again. The board is also open, so it would be a lot easier for me to write. Uh, so the thing that was happening was that in ionic lattice, the positive and negative ions are all attached to or joined together by ionic bonds, and the ions scatter and they mix with water. So all the ions they get scattered by the vigorous force of stirring. The positive and negative ions they dissociate. And water molecules come in between, which is why they're not able to get back together again. They get completely surrounded by water molecules, and that's how a normal ionic crystal dissolves. And I had made this Hess cycle. Okay, remember this is the Hess cycle for substances that are dissolving. And enthalpy change of solution is basically equal to the negative of lattice energy plus the enthalpy change of hydration. Okay, is this clear? Sarah, is this clear? Abu Rera, clear?
Yes, sir.
Okay, so one path is equal to the other path. Now the thing is, what happens when you move down the group? Focus on the enthalpy of solution first. The first comment is going to be that if enthalpy of solution is very endothermic, okay, now this could get confusing. The explanation for this is kind of confusing. So if enthalpy of solution is endothermic, that means the substance is not going to dissolve until it gets some energy. So the substance is not very soluble. I mean, the entire process of dissolving requires energy. Okay, for example, calcium carbonate or limestone. There are lots of salt crystals that are not very soluble. I mean, which are not very soluble. For example, if the positive and negative ions are attracted to each other very, very strongly, so your stirring would not dissociate them. It would be very hard to actually break them apart. I mean, there are a lot of ionic crystals which are very, very strong. Marble is one. Marble is calcium carbonate. It's calcium 2 plus and carbonate minus 2. They attract each other so strongly that your stirring is not going to actually break a piece of marble. Like put a piece of marble in water, no matter how strongly you stir it with a spoon, it's the particles are not going to dissociate, right? So so this lattice energy, okay, I'm going to go into a lot of details with this. So this lattice energy, where you have to break the lattice, it depends on two things. One of them is it depends on the strength. So it depends on the strength of the lattice. How strongly are the positive and negative ions are attracted to each other? So remember, there are two factors: greater charge on ion. That's factor number one. So if the ions have a very large charge, for example, aluminium is +3, then it's going to attract the negative ion very strongly. And you're stirring with a spoon, that's not going to break the lattice. It's not going to dissociate the lattice. Uh, so compounds that have larger charges, they're not very soluble. Compounds that have smaller charges are more soluble because they break easily. Like NaCl is very soluble. Why is it soluble? Because +1 and -1, they don't attract each other very strongly. So that's one factor: greater charge on ion. And the second factor is the size of the ion. Smaller ions are closer together, so they attract each other more. So these two factors would lead to a stronger lattice. That means larger lattice energy. You would need a lot of energy to actually break this lattice. So an example is uh, NaCl. The lattice of NaCl, where Na plus 1 and Cl minus 1 are attracted to each other, so it's a giant ionic lattice. That could be broken very, very easily. Okay, so it's very easy. You stir a spoon and the ions, they just scatter. They all dissociate. The ionic bonds, they break. But on the other hand, if you have MgO, MgO is a very, very strong lattice. it's Mg2 plus, O2 minus, and O2 minus is then attracted to Mg2 plus again, and Mg2 plus is again attracted to O2 minus. So it's a giant ionic lattice of positive and negative ions, and it's going to be very hard to actually break this. This is a very strong material. It's used in furnaces because it's not going to melt. It's not going to break easily. NaCl breaks easily. It has a low melting point. MgO doesn't. Very, very strong. The same is the case with aluminum oxide. Aluminum is +3, oxygen is -2. So it's going to be a very strong lattice. Is this point clear to everyone?
Yes, sir.
Yes, sir.
So the first step is to dissolve an ionic compound. The first thing is you would have to break the lattice. That's the negative of lattice energy. And that requires, sometimes it requires a lot of energy, sometimes it doesn't require a lot of energy. It depends on these two factors. The next part is once the bonds have been broken, uh, once the ions have scattered, they should be able to attract water molecules. That's the next part. That once Now I'm going to talk about comment on enthalpy of hydration. So I'm going to comment on this. So enthalpy of hydration. Once the ion is free from the lattice, like if you have a positive ion, then why would water molecules surround it? Let's say a positive ion has broken free from the lattice. The reason it's going to surround it is that oxygen is a polar molecule. So the lone pairs of oxygen are going to be attracted to the positive ion. And usually a complex is formed. So that's enthalpy of hydration. That once an ion breaks away, it gets surrounded by water molecules and it turns into an aqueous ion. So that's enthalpy of hydration. And again, enthalpy change of hydration is going to be more exothermic if the ion is smaller. If it's smaller and it has greater charge. Smaller ions, they always make, and if it has greater charge as well, for example, if it was +3 over here, then it would attract water molecules very, very strongly. So stronger attraction for water molecules. So there's going to be a lot stronger attraction for water molecules. So two things are happening. One is you break the lattice. The other one is hydration. Okay. So is this clear up till this point? The factors that lattice energy depends on and the factor that hydration depends on. Aisha, is this clear?
Yes, sir. So, enthalpy of hydration will be more exothermic down the group of sulfate solubility.
So now I'm going to comment on that. So what happens when you move down the group? Now we're talking about MgSO4. Remember the first part, forget the negative sign, ignore the negative sign. The first part is actually endothermic. By definition, it's negative. But otherwise, this value is actually positive because the lattice energy is the arrow pointing in this direction. So because the arrow is you're breaking the bonds, that's why by definition you call it the opposite of lattice energy, the negative of lattice energy. So in fact, it's an endothermic part. You're breaking the bonds, it's endothermic. And over here, you're forming bonds with water. Once the gaseous ions are dissociated and the water molecules that come in, they get attracted to the ions and they form bonds with it. So that's bond formation. That part is exothermic. So one part is endothermic, the other part is exothermic. Now, remember, if the enthalpy of solution overall is endothermic, that means it's not going to be very soluble because the reaction would not happen. The dissolving process is not going to happen since it requires energy. Just one second. So if enthalpy of solution is coming out to be endothermic overall, this entire process dissolving, that means it's not going to dissolve. It needs energy to dissolve. And vice versa, if it's coming out to be exothermic, that means it's going to dissolve. So it depends on this one part which is endothermic, you need to break the bonds, and the other part is you need to form bonds with water molecules. So it depends on these two values. One is exo, one is endo, the other one is exo. So what happens down the group? It depends on these two things. You break the lattice, and then you form bonds with water. So this part is actually endo, and this part is actually exo. What happens down the group in group two? When you move down the group, and we are
Reactivity
comparing,
increases.
no, when you move down the group, for example, there's Mg. I mean, he's talking about MgSO4, and
Solubility decreases.
solubility decreases. Now, so you're moving down the group, right? You're moving from MgSO4 to BaSO4. So what's the difference between Mg and Ba? Mg is they have the same charge, everything is the same. The lattice is exactly the same, except for one major difference, and that is that Mg is a smaller ion. And Ba is a so Mg is a smaller ion and Ba is a bigger ion. So smaller ions they make stronger lattice. So this is stronger, and this is a weaker lattice. So when you move down the group, the ion size increases. You have a bigger ion and you have a smaller ion. So when you move down the group, two things happen. Not only does the lattice energy decrease because it's a weaker lattice now, it would be a lot easier to break. But the ion would be bigger and it would not be attracting water molecules that strongly. So even the enthalpy of hydration would decrease. So what you're going to write over here is, I mean, the first part is you're going to mention that down the group, delta H solution becomes more endothermic because the solubility is decreasing. Okay, this is what we mentioned. That if the enthalpy of solution is endothermic, then it's not going to be very soluble. So down the group, BaSO4 is not soluble, MgSO4 is soluble. And then you're going to mention the other thing, which is down the group, the ion size or the cationic radius is increasing.
So, and lattice of barium sulfate is bigger, right? So this means it's easier to break it. It's
Huh.
not that strong like magnesium sulfate, but why still it is insoluble.
Okay, I'm explaining that. Okay. So down the group, the cationic radius increases actually. The ions become bigger. Okay, that means so both lattice energy and enthalpy of hydration both decrease. Okay, so both of them decrease. BaSO4, it would be a weaker lattice, it's a bigger ion, and it's not going to attract water molecules that strongly, so the enthalpy of hydration would be lesser as well. Sakib, is this clear? Okay, both are decreasing.
Yes, sir.
Acha, but we have just stated that enthalpy of solution is becoming more endothermic. So enthalpy of solution is the sum of the endothermic part and the exothermic part. So if it's becoming overall, if it's becoming more endothermic, that means both of them are decreasing. This is decreasing. Down the group, it decreases, and this also decreases. Down the group, like if instead of Mg you had barium, both of them would decrease. But since it's becoming more endothermic, that means this term over here is not decreasing as much as this one. Okay, this term is relatively bigger and this term is relatively smaller. That's why enthalpy of solution overall is coming out to be endothermic. That the endothermic term is bigger and the exothermic term is smaller. So if you sum them up, the overall enthalpy of solution comes out to be endothermic. Sakib, did you get this point?
Yes, sir.
Okay, so it's becoming easy to break the lattice down the group. But because it's a bigger ion, it's not forming bonds with water. It's not getting surrounded by water molecules, which is why it's not dissolving. Okay, bigger ions, they don't attract water molecules that strongly. So, so the point is both lattice energy and enthalpy of hydration decrease. And the last point is going to be that the lattice energy decreases less compared to enthalpy of hydration. Theo, that's the last point. That both of them are decreasing down the group. You have bigger ions, a weaker lattice, easier to break, but the ion is bigger, so it's not going to attract water molecules. So the bonds formed, they won't be that strong. It won't be that exothermic. So both of them are decreasing down the group. But since the solubility overall is decreasing, enthalpy of solution is becoming more and more endothermic down the group. That means this part is decreasing less. This is relatively bigger, and this part is decreasing more. This is relatively smaller. So that's the last part. That lattice energy decreases less compared to enthalpy of hydration. Is this clear?
Yes,
Yes, sir.
TK, and remember, for the same question would come for hydroxides. TK, for hydroxides is the opposite. For hydroxides in group 2, when you move down the group, magnesium hydroxide is not soluble, but barium hydroxide is actually soluble. So everything would be exactly the same. You're going to write the same statements. Exactly the same statements would be written. Uh, but except for this one, that enthalpy of solution is becoming more exothermic, because for hydroxides the solubility increases down the group. So the enthalpy of solution is becoming more and more exothermic. And why is it becoming more exothermic? This is decreasing and this is also decreasing. But this over here is decreasing more compared to this one. Okay, so the last statement would be the opposite for hydroxides, which is why for hydroxides the solubility actually increases down the group. Okay. Now, and it would be best, my advice would be, I mean, you need to know the whole cycle, you need to know the whole concept. But since this could get very confusing, uh, make sure you remember these 3 points. You're going to get this very typical question that usually comes in every paper, and they want a comment on the enthalpy of they want a comment on the solubility of hydroxides down the group or the solubility of sulfates down the group. So it's better to actually just remember these 3 lines, and remember the fact that for sulfates the lattice energy decreases less compared to enthalpy of hydration, because in the paper you can't really think all of this. Even if you know the concept, it's going to be very hard to actually think of this and get this right. So just make sure you remember this. It's a very typical question that comes very, very often. As the next part is, we're just going to do this one. State and explain the relative. Next question. State and explain the relative acidities of ethanol and phenol. So relative acidities. Both of them have an OH group. You have ethanol, which is CH3, CH2, and OH. It dissociates and produces H plus 1 ion. And you have phenol. Phenol does the same. So you have a benzene with its electron cloud, and there is an OH. Now the question is, who's going to dissociate more? And which one is relatively a stronger acid?
Benzene is stronger acid, I guess.
ठीक है.
Phenol is stronger acid than ethanol.
ठीक है. So phenol is a stronger acid. There's a table actually that you have to remember as well, that alcohols are not really acidic. I mean, they only react with sodium. Phenols are kind of slightly more stronger acids. They react with sodium as well as sodium hydroxide bases as well. And then you have carboxylic acid as well. That's a full acid. That reacts with carboxylic acids react with sodium. They also react with the base sodium hydroxide. They also react with sodium carbonate. I said, so what's the reason for that? They're asking for the explanation. The explanation is that you have a carbon chain which has an electron donating effect. And because of that, the negative charge over here, it becomes bigger. The negative charge density increases. And if the negative charge density increases, it's going to attract the H+1 back again. It's not going to dissociate. What happens in phenol? In phenols, the oxygen has a negative charge, but the lone pairs, they start to overlap with benzene's electron cloud over here, which is why the negative charge becomes a lot smaller. It gets, the density decreases. It gets distributed over the benzene ring. So the negative charge is not able to attract the H+1 back again. So more dissociation happens.
Sir, can we say the oxygen has been partially delocalized with the benzene ring, the electron cloud of the benzene ring?
I mean, the way you're going to write the answer is exactly the same. You're going to write, I mean, for example, over here, you're going to write the statement that you're going to talk about the alkyl chain having an electron donating effect, which increases the charge density over here, or you can say that the ion becomes unstable. And for this one, for phenol, you're going to write that the lone pair on oxygen, it overlaps with benzene's electron cloud, which is why the charge density over here decreases and more dissociation happens. There's less attraction for H+1 ions. So we can also have a look at so these are the two statements that you're going to write. We can have a look at the marking scheme as well. I mean, one mark was for phenol being more acidic, and the other one is about the electron donating group in alkyl chain, and the lone pair of electrons on O. This is the other point that is delocalized with the ring benzene electron cloud. So that's one mark. Is this
So
clear?
can we also mention about the Ka value?
No, you don't have to mention the Ka value over here because
Okay,
they didn't ask for that. It's just a 2-mark question. So you don't have to go into a lot of detail. Just 1 mark. I mean, 1 mark was for the relative acidities. This was less acidic. This was more acidic. The other mark was that the carbon chain is electron donating, so the negative charge density increases, or you can call it that the ion is less stable. It would attract the H+1. And over here, you have to mention that the lone pair overlaps with benzene's electron cloud, or and it becomes more stable. The charge density decreases, and it's not going to attract the H+1 that strongly. Okay, that's it. So let's continue with this from the same question next class. Okay.
Okay, sir. No.
Thank you, sir.
Okay, then take care.
Oops.
Hafiz.
Enough.